What's up, physics fans? Here we go for another one. This is Physics 12, Static Equilibrium chapter. This is on page 38, question number 2, a nice review question. It's a ladder question. A uniform 15-kilogram ladder that is 5 meters long stands on the floor and leans against a vertical wall, making an angle of 25 degrees with the vertical. If the friction between the ladder and the wall is negligible, what is the amount of friction between the ladder and the floor that'll keep the ladder from slipping? So the ladder is leaning on the wall. So the wall is pushing back on the ladder. F wall. Now this is a normal force perpendicular to the surface. And we're also told that there's no friction on that surface so that it can slide up and down without resistance. So the wall's pushing back. This is also a 15-kilogram ladder. So in the center of gravity, So gravity's pulling down on it. It is sitting on the floor, so there is a normal force upward. And there's one more force. It says, what is the minimum amount of friction between the ladder and the floor? So there's friction on the, which way is that friction? Well, this ladder wants to slide out. How do you know? Well, it has a force pushing on it, F wall. So there's a force pushing that way, and if there's no resistance to it, it will slide out and it'll fall down the wall. So there is a frictional force along the floor, perpendicular to that normal force. So there's our forces. Let's get rid of the wall so that we can focus on what the question's asking for, the ladder. So select that, delete that. Oh my goodness, that looks like a free body diagram, and it is. Those are the free body pictures. The arrows that represent the forces acting on it. Do we know any of these forces? Well, we only know one of them right now. And we can quickly figure that out by that it's a 15-kilogram ladder, and the force of gravity on it is mg, 15 kilograms times 9.8 newtons per kilogram. That's the gravitational field strength. This becomes 147 newtons. So we know this force. Okay, I'm going to ruin our free body diagram by writing some numbers in here. So this is 147 newtons. It says 25 degrees with the vertical. So this is 25 degrees. So this is also 25 degrees because that is the vertical force, the gravitational force. So it's 25 degrees there. This is also 25 degrees, alternate interior with parallel forces. And this is 65 degrees because it's at a right angle and they have to be complementary. And also this angle is also 65 degrees. I've totally ruined this free body diagram by writing all over it. Might as well continue on. And it's a 5-meter ladder, so this midway point is 2.5 meters. From where? We have to choose where the pivot point is going to be. I kind of like putting the pivot point where I destroy the most torques. What do you mean by destroying most torques? Well, this is the torque formula. The torque is force times distance times the sine of the angle between the radial arm and the force. The only way to make that 0, get rid of the torque, is put the angle to be 0, or where the force is applied at the pivot point. So if the force is applied at the pivot point, there is no torque. So that just screams to me, make that the pivot point, because then I get rid of those two forces. Okay, so let's do the sum of the torques at that point. Sum of the torques has to equal 0. We're going to put the pivot point at the bottom. So the pivot point is at the bottom. So the torques clockwise has to equal the torques counterclockwise. And the torques clockwise are these ones going that way, and that'd be the force of gravity. And the torques counterclockwise is this wall force. Okay, because that makes it go counterclockwise around the pivot point. So the clockwise is the torque caused by the ladder. The ladder's gravitational force. So I should have probably just done it slightly different. I should have probably done by the force of the cog. And that has to equal the torque caused by the force of the wall. So the formula is force times distance times the sine of the angle. That has to equal force times distance times the sine of the angle. Okay, let's just do a quick one for the center of gravity. So this is the radial arm. And the force of gravity is pulling down at that point. So this is the angle that we want between those two ones. There's the pivot point. And that's the radial arm, that's the force. So that's the angle that we want. And it is drawn on there to be 25. So let's fill it in. This is the COG, and this is the F wall. This will be 147 newtons times the distance to it is half the length, which is 1/2 of 5 meters, and times the sine of the angle, which is 25. Okay, let's just line that all up. I'm going to move this over for a bit. There we go. Change equals the force of the wall. We don't have that. Times the distance away, 5 meters, times the sine, 65. Okay, so we'll take 147 times 2.5 times the sine of 25. And this is 155.3 Newton meters. And that has to equal F wall times, and I'll just multiply those together, 5 sine 65, and that is 4.532. And that'll be the unit of meters. So if we have to now pull it all together, we take the 155.3 Newton meters, which is the torque caused by the force of gravity of the ladder, and it has to balance the torque caused by the wall up top, which is this. So we take the 155 and divide that by that, and we get the force of the wall is equal to 34.27 newtons. Now, it didn't ask for the force of the wall, so we'll continue on with static equilibrium's other component. This is the sum of the torques equals 0. We have to do the sum of the forces. So let's do the sum of the forces in the x direction, because that's where the F wall is in the x direction. So we'll sum of the forces in the x direction also have to equal 0. That's the translational equilibrium. So the forces left have to equal the forces right. And the forces left is F wall. And the only force that's to the right here is the frictional force. So that has to equal the force of friction. This is 147 newtons. So the force of friction, F wall is not 147. Oh, undo. The F wall is 34.27. So that has to equal the force of friction. Dun, da, da, da. That's it. That's the question. Now, there's more to do. If we wanted to science the snot out of this and get more out of it than we've already done, we could get some more. We can go further. And I'm just going to do that right now. Just boxing off the things that I've already done, and that you see that's all that's necessary to get the answer. But let's do the sum of the forces in the y direction. Sum of the forces in the y direction have to also equal 0. That means the forces up equals the forces down. And the forces up is the normal. And the forces down is the center of gravity. The two forces, let's just highlight them in green. This is the upward force, and this is the downward force. And they have to balance. So from this, we get that the normal force is also 147 newtons. And from this, we can use the force of friction is equal to mu times n, the normal force pushing the two surfaces together. And what's so cool, we have this number, we have this number, so we can calculate what mu is. And mu is just going to be the force of friction over the normal force. And the force of friction is 34.27 newtons. And the normal force is 147 newtons. Mr. Calculator, take that number that we have, 34 divided by 147, and that is the coefficient of friction. The minimum coefficient of friction necessary to stop this ladder from sliding out. That's the coefficient of friction necessary to stop this ladder from sliding out due to its own weight. But that's not what the question asked for. But I just wanted to show you we could go further and get so much more information. And we can even make this more challenging of a question by having someone climb the ladder. And as someone's climbing the ladder, we can figure out what happens to the minimum coefficient of friction necessary. That's in another, and I'll put that in the link in the description below. Subscribe, like, smash that subscribe button and like. Anyways, thank you. Have a great day.